Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 6 of Module 2. So friends, in previous lecture we have seen the reference electrode as hydrogen electrode and we have seen its advantages and its disadvantages. Now we will see one of the widely used reference electrode, that is calomel electrode. This electrode is very widely used in the laboratory because of its convenience as compared to hydrogen electrode. We have seen the construction of calomel electrode in our previous lecture. We have seen it in short. You can see here the figure of calomel electrode, and there are various advantages of this calomel electrode over the hydrogen electrode. So this reference electrode, because of its portability, is very utilizable and very convenient to handle. Basically, as we have discussed earlier, this calomel electrode, it consists of a glass tube containing pure mercury at the bottom and a paste of mercury and mercurous chloride. It is called as calomel, isn't it? This is mercury. This is mercurous chloride and mercury. So, as we have discussed in earlier lecture, you have to, we have to thoroughly mix this mercury with this mercurous chloride, say for 2-3 days in mortar and pestle manually if you are preparing it in laboratory, and then you get the calomel paste which is placed over this mercury, and then remaining tube is filled with the KCl solution of known concentration. Usually we take the saturated calomel solution, or usually we take the saturated KCl solution, and we call it as a saturated calomel electrode. The side arm is actually provided for the connection of electrode to the another electrode, and a platinum wire is used for the electrical connection to the external circuits. Okay. Now, if you look at this equation, you can use this electrode as a half cell to any other half cell. So, if you are utilizing it for the anode, or if you are utilizing it as a cathode, the both way it can act. So, when you want to use it as anode, it will be connected to some other half cell which is actually acting as a cathode, and if you want to act as a cathode, you have to connect this to the some such cell which can act as anode. That means some in case where the calomel electrode is connected to another electrode, an oxidation reduction reaction takes place. So if it is connected to such a cell where the other half cell is cathode, so this cell will act as anode and the oxidation will take place here. So now, in order to have the oxidation at this particular calomel electrode, we need to see who is going to supply the electron. If you look at this electrode, here it is a KCl, K plus and Cl minus. Obviously, both of them, they cannot supply the electron. The paste is mercurous chloride and mercury. Obviously, they also cannot supply the electron. So, who is going to supply the electron? This mercury is going to supply the electron in case if I connect it on the left hand side electrode. Okay. And this mercury can then be supplying the electron, and then the chlorine from, chloride from this calomel paste, it can actually take the chlorine and that can gain the electron. So the overall net reaction, if I am connecting it to the anode, will be twice Hg, that is in liquid form, plus twice Cl minus, which is from aqueous solution we are getting from the top, and then it will give you Hg2Cl2 solid and then 2 electrons. So this is a liberation of 2 electron, and therefore thereby it will act as an anode. Okay. Now, this equilibrium sign is shown just for the sake of understanding that it can also act as a cathodic electrode. If I connect it to some such electrode wherein it has to gain the electron, in that case, I will reverse down this reaction, Hg2Cl2 solid plus 2 electron, and it will give twice Hg liquid plus 2 Cl minus aqueous. So this way also we can do. I mean, from right to left also it can go. All in all, if I use it as anode and if I connect this cell to some cathode, so Nernst equation for this electrode at 25 degrees centigrade will be given by, now E is equal to E standard minus 0.0591 upon 2 log of 1 upon Cl minus square. If I follow this reaction, because my mercurous chloride is solid, and therefore the product upon reactant if I take, so since this is solid, it is 1, and therefore this Nernst equation can be given by this. That means the potential actually depends on the chloride ions. I mean to say that the concentration of KCl solution. Now depending on the concentration of KCl used, the calomel can behave as of three types. So basically, as I said, if I use the saturated KCl solution, I can call it as a saturated calomel electrode SCE, which is the most widely used calomel electrode. And in this saturated calomel electrode or saturated KCl solution wherein used, we call it as a saturated calomel electrode, and its oxidation potential is actually minus 0.2415 volt at 25 degrees centigrade. If I use decinormal calomel electrode, that is, if I use the KCl solution of 0.1 normal, its oxidation potential becomes minus 0.3338 volts at 25 degrees centigrade, and we call it as a decinormal calomel electrode. Whereas if I use the 1 normal KCl solution here, so its oxidation potential becomes minus 0.28 volt at 25 degrees centigrade, and this electrode is called as normal calomel electrode. One needs to be very careful while using this terminology, because in electrochemistry or in potentiometric titrations, this calomel electrode are widely used. In potentiometry, this calomel electrode is widely used, and what kind of calomel electrode you are using, one has to be very careful. In majority of the cases, we use the saturated calomel electrode, and therefore we recommend that this saturated calomel electrode potential, one has to mug up, one has to keep in always in mind that the standard potential is 0.2415 at 25 degrees centigrade for this saturated calomel electrode, and then this can be utilized anywhere for the further calculations in applications of potentiometry, isn't it? So this is how this calomel electrode, reference electrode, is much more wider, widely used than the other reference electrode. The other famous reference electrode is obviously silver chloride, but then again this calomel electrode is very cost effective, and this calomel electrode is widely used among all the laboratory purpose. In comparison to hydrogen electrode, if you see, there is no limitation, like you have to maintain the pressure. Like in hydrogen electrode, you have to maintain the pressure at 1 atmosphere, you have to maintain, you have to get the dry and pure hydrogen gas, and all those disadvantages which are associated with the standard, which are associated with the hydrogen electrode, hydrogen reference electrode, all these are eliminated over here, and you can very easily take it in your pocket. That means it is a portable calomel electrode, you can take it anywhere. The only thing is you have to put this KCl solution maintained at the top level, and you can very easily use it. Also, depending on the consumption of this calomel paste, I mean, if this calomel paste is reducing while attached to some other half cell, so I can actually predict whether it is behaving as anode or cathode, or if the volume of this calomel paste is expanding, so I can very easily predict uh, using the simple Nernst equation. I can easily predict that the given electrode is connected to an anode. Thereby, this calomel electrode is of very much of use. Okay. Now, friends, so far what we have seen, so far we have considered the electrochemical cells in which the EMF is generated due to two different chemical reactions which are taking place at two different electrodes. Now, such cells are called as chemical cells. However, it is possible to construct a cell with same electrode and same electrolytes on both sides. That means if I want to use the same electrode dipped in same kind of electrolytes on these both the half cells, in that case also I can utilize the concept of determining the EMF of this cell. The only thing is what I will have to do, I will have to make the concentration of both the cells in which the electrodes are dipped different. So the cell in which basically the EMF is produced only due to the difference in concentrations of the electrodes or the electrolytes, which are they are called as concentration cells. Basically, I mean to say that in chemical cell, like EMF is generated due to chemical reactions taking place at two different electrodes. On the other hand, in concentration cell, EMF is generated due to the transfer of matter from higher concentration region to lower concentration region. Also, it would be useful to state here that in case of concentration cell, because as both the electrodes are same, the concentration difference would make the potential difference across the two half cells, and thereby we can find out the EMF of the cell. Now, based on this concept, these concentration cells can be classified into two types. One is wherein the electrode concentration is different, and secondly wherein the electrolyte concentrations are different. Now, the second case wherein the electrolyte concentrations are different, we can further utilize this concept for further two sections like electrolyte concentration cell with transference and without transference, that we will see subsequently in this lecture. However, first herein let us see the electrode concentration cell. So now you can see over here, this is electrode concentration cell. So in this cell, the concentration of electrolyte is same, but the concentration of electrode is different. Now, how can it be possible? It is possible. Usually in such kind of situation, it is possible only in case of gas or amalgam type of electrodes. Now, if I say you consider this cell, which is represented by this equation 45. So platinum in contact with hydrogen gas, and which is in contact with the hydrogen ion at one concentration, and then the same in the same solution, the other platinum electrode which is at other pressure, that is the hydrogen gas at other at different pressure is attached. So basically in this cell, one electrode is at pressure P1 and other electrode is at pressure P2. Now in this kind of cell, the two hydrogen electrodes are dipped in the same solution containing the hydrogen ion, like if I take HCl solution. So the reaction taking place are usually like this. If you can say that at left hand side electrode, this hydrogen will liberate the electron and giving to hydrogen ions, and these two electrons are liberated. Whereas at right hand side electrode, these two electrons are being consumed and then the hydrogen gas is produced. So the net reaction will be hydrogen at pressure P1 leading to hydrogen at pressure P2. And therefore the cell EMF will be given by E is equal to E standard minus 2.303 RT upon 2F log of P2 upon P1. You can take over here NF. So E standard, that is the EMF of standard cell for concentration cell is 0. This we know, and therefore E is equal to 2.303 RT upon 2F into log of P1 upon P2. Straight away I can calculate if I know this. So little simplification will give me this kind of expression. Okay, that means the cell EMF is positive if my P1 is greater than P2. You can see from this equation. That means in such cases the process is spontaneous and gas expands from higher pressure P1 to lower pressure P2, and vice versa is the case. Okay. Similarly, the other type of cell is amalgam electrode cell. If I consider this particular cell, wherein lead mercury at concentration one concentration is in contact with lead ion, and which is in contact with the other lead mercury cell at different concentration. So these two electrodes at different concentration, they are dipped in the lead ion solutions. So at left hand side electrode, your lead mercury at one concentration will lead to oxidation. That means lead ions are liberating and two electrons are liberating there. And at right hand side electrode, these two electrons are absorbed by the lead ions and lead mercury amalgam is released. So the net reaction will be lead mercury at concentration C1 will give you lead mercury at concentration C2 and vice versa. So the cell EMF will accordingly be in forward direction will be E is equal to E standard minus 2.303 RT upon 2F log of C2 upon C1 product upon reactant. So I can get E is equal to in this simple manner 2.303 RT upon 2F into log of C1 upon C2 because E standard for concentration cell is 0 and at 25 degrees centigrade I can rearrange this. Therefore, if you look at this particular equation, I can very easily predict that the cell EMF is positive if my concentration of first cell electrode is greater than concentration of second cell electrode and the whole process is spontaneous. That is basically lead goes from higher concentration amalgam to lower concentration amalgam, which is quite obvious. Now, the another type of concentration cell is electrolyte concentration cell. In these types of cells, the concentration of electrodes are same, but that of the electrolyte concentration is different. Now further, they are also of two types. One is electrolyte concentration cell without transference and other is electrolyte concentration cell with transference. Let us have a look at electrolyte concentration cell without transference. Now, in this type of cell, there is no transfer of ion from one half cell to other half cell basically. And the two electrodes are separated by salt bridge. You can see over here. Okay, look at electrodes. Both are platinum electrodes which are dipped in at the particular pressure in presence of hydrogen, and this is a glass tube wherein the hydrogen pressure is maintained, and it is dipped in two different concentrations of hydrogen ion at one concentration and other concentration. Okay, now this is connected through a salt bridge. Now consider two electrodes at one atmospheric pressure which is dipped in two different hydrochloride solution having different concentration, which is connected by a salt bridge, and the cell reaction will be represented by this particular equation. That is platinum in contact with hydrogen at 1 atmosphere, which is in contact with hydrogen ion at platinum electrode at uh, hydrogen of 1 atmosphere, which is in contact with hydrogen ion at one concentration and which is connected through salt bridge with the other hydrogen ion solution at different concentration, in which the platinum electrode at the same pressure of hydrogen is dipped in. Okay, so what is the reaction at left hand side electrode? Basically, at this electrode, the oxidation will take place. So hydrogen at 1 atmospheric, it will lead to 2H plus 2 electron, and the 2 electrons will be lost. These electrons will be gained at the right hand side electrode, and hydrogen is released. So the net reaction will be hydrogen ion at concentration C2 will give hydrogen ion at concentration C1. So the cell EMF will be given by E is equal to E standard minus 2.303 RT upon 2F log of product upon reactant. So the little rearrangement will give me this particular expression of 53. And at this stage, I can actually say, if you look at this equation, the cell EMF will always be positive if my concentration of C2 is greater than C1, and vice versa is the case. So this way I can use the electrolyte concentration cell without transference. I can utilize this concept to find out the EMF of the cell. Similarly, the other case, if I see the electrolyte concentration with cell, previously it was without transference, it is with transference. So look at this particular figure. In this figure, the electrolyte concentration cell with transference, what we say, you can see this U tube kind of arrangement. In this particular type of arrangement, the concentration of electrode is same again, You can see over here, like in previous arrangement, it is given, and the concentration of electrolytes is different, and the electrolyte are in direct contact with each other, uh, which is called as through this particular liquid junction. Through this liquid junction, they are in direct contact. So if ions can diffuse through this liquid junction, if ions can diffuse through this liquid junction, transfer of ions can take place from one part to another part. Okay, so this is interesting. Now consider two hydrogen electrode at 1 atmospheric pressure dipped in two different HCl solution. This is one concentration, this is other concentration. Now they are in direct contact with each other, and the cell reaction in such case will be represented by this particular cell. This is one half cell, this is other half cell. So platinum electrode, which is encapsulated in one glass tube at hydrogen pressure of 1 atmosphere, and which is in contact with the H plus ion concentration, that is HCl at concentration C1, which is connected to this through the liquid junction with the other concentration cell, that is HCl at concentration C2, and in which the other platinum electrode which is encapsulated in the hydrogen at 1 atmospheric pressure. So this is the complete cell reaction. Now at left hand side electrode, again the same thing will happen. The hydrogen at 1 atmospheric pressure will give you twice H plus plus 2 electrons, and the released 2 electrons will be absorbed at the right hand side electrode, and hydrogen will be released. So the net reaction will be H plus at concentration C2 will give to H plus at concentration C1. Now now if you see left hand side electrode is negative electrode, while this your right hand side electrode is positive electrode. So this is your positive electrode, this is your negative electrode. So electron flow in external circuit from left hand side electrode to right hand side electrode. You can see over here, from left hand side electrode to right hand side electrode. However, in solution there are no electrons. So chloride ions transfer from right hand side to left hand side in the solution, from this side to this side. Now why this will happen? This will happen in order to complete the circuit, so that electron can flow from the external circuit. So this way the circuit will be completed. Now at the same time, equivalent number of hydrogen ions move in the opposite direction. This is quite obvious, isn't it? Equivalent number of hydrogen ions will always move in the opposite direction to that of chloride ions. So now if T plus and T minus, if I represent T plus and T minus as the transport number of say H plus and Cl minus ions, so these processes can be shown by this particular equation. You can see the transport number of chloride ions at concentration C2 will lead to transport number of chloride ions at concentration C1. That means the chlorine ions from at C2 concentration will transfer from this C2 concentration to C1 concentration, and the transport number of this H plus ions at C1 concentration will transfer from left hand side to right hand side through the liquid junction potential. That is what is given. However, I know that the transport number of cation is equal to 1 minus transport number of anion. So if I substitute this value over this equation 56, I get this particular equation. So 1 minus T minus in bracket. So H plus at C1 concentration will give you 1 minus T minus, that is transport number of anion, into H plus of H plus at concentration C2. So these hydrogen ions, they are transferring from left hand side to right hand side. The only thing is the multiplying cationic transport number has been represented like this. Okay, so the net reaction is the addition of this your equation 55, 56 and 57. So if I would like to write down this, it will give me this kind of the complete reaction. That means hydrogen ion at higher concentration plus chloride ions at lower concentration multiplied by transport number of anion plus hydrogen ion at lower concentration minus this hydrogen ion at lower concentration into transport number of anion will lead to this particular part. This is simple algebraic rearrangement of what is given with this, I mean, addition of 50 equation 55, 56 and 57. So ultimately what I get the transport number, I mean, the hydrochloride acid at higher concentration is transferring from the lower concentration at this end. So this way I can utilize this particular concept in this electrolyte concentration with transference. I can utilize the concept of transport number and how they are transferring inside the solution that I can calculate in this particular type of cell. So what that means, we can now utilize this concept to basically find out the EMF of the cell of this type, that is the electrolyte concentration cell with transference. So the cell EMF, how it can be given? It can be given with the help of Nernst equation. So that is E is equal to E standard minus 2.303 RT upon F log of C2 upon C1, log of C1 upon C2 to the power the transference number of anion. Now, which can alternately be written as this, particularly of type equation 59. This particular equation can be utilized further in this fashion, and we can obtain the expression for getting the EMF of the cell. Now, I can write down this expression in terms of the transference number of anion. I can write down the same expression in terms of transference number of cation in this particular manner. However, the interesting thing is to see that in order to have the EMF positive, always my concentration of this right hand side cell C2 should be higher than the concentration of this left hand side cell. That is one of the basic criteria for obtaining the positive EMF. That is what is the utility of this electrolyte concentration cell with transference. Basically what we have seen in this type of transference cell, or this type of electrolytic concentration cell, basically we have seen that the two equivalent half cells of the same composition differing only in terms of concentrations, and they constitute basically a concentration cell. Now a limited form of kind of galvanic cell is it. It is always easier to calculate the potential developed by such a cell using the Nernst equation. Now, when the concentration of reactant in both the half cells they are equal, a concentration cell produces a small voltage as it attempts to reach to the chemical equilibrium, whatever is the occurring reaction. Now, in thermodynamics also, in terms of thermodynamics, if I would like to talk, in thermodynamics, the free energy of the electrochemical system, a concentration cell generates electricity from the reduction or the cell reaction at right hand side as the difference in the chemical concentrations in the two half cells, which is basically reduced at that particular electrode. Now the energy is generated from the thermal energy that the cell absorbs at heat as the electricity flows. This generation of electricity from ambient thermal energy without the temperature gradient is possible because of the convergence of chemical concentration in two half cells. They particularly increases the entropy, and this particularly increase more than compensate for the entropy decrease when the heat is converted into electrical energy. That is the thermodynamic aspect of this kind of cell. Now, what are the applications of concentration cell? These type of concentration cells, basically they can be utilized for say pH meter. pH meter is the specific example of the type of concentration cell that is used to determine the acidity or the basicity of the specific solution. Secondly, the concentration cells are used in the cell reactions uh, where ion selective electrodes are required to bring about the electrolysis or any other electrochemical reaction. So these are what the examples, these are what the utilizations of these concentration cells. So friends, we will stop here in this lecture. In our further lecture, we will see some of the numericals based on these applications, actually based on these different types of electrodes that we have seen. And what we will do, we will also try to see some of the applications of these uh, electrodes, different types of electrodes that we have seen. We will try to see the different methods for determination of pH as well, using different types of electrodes, whatever we have studied in previous two lectures. So thank you, friends.